Any other questions before we begin? Alrighty, so we're just going to talk about some isomers. So in the first one, they give us 6 different types of isomers. One of them is already identified, hydration isomer. You guys didn't explicitly go over what hydration isomers were. You don't need to know them. That's why it's the example, but it's just moving around waters. That's it. So example A, that's just to show you how this problem is done. So if we go on to B, then what we see is we have a cobalt diethylamine complex and a chromium cyanide complex. And all we're doing is switching the metal. That's all we're doing here. So what do you think it's going to be if we're just switching the metal? We're changing its coordination sphere. So that might give it... Yeah. So the coordination sphere is what it's coordinated to. So in both of these cases, we have En. It just changed colors randomly. Okay. In both these cases, we have En and our Cn. And all we're doing is changing the coordination sphere of each metal. So one of them originally was bonded to 3 ethylene diamines, and now it's bonded to 6 cyanides, and then vice versa for cobalt. So B is coordination sphere because we're coordination isomers because we're changing the coordination sphere of it. Now for C, I made it a little bit easy. I bolded the ones that we need to look at. So we have 2 cyanides up and down, then 2 cyanides next to each other. Cis and trans, yeah. So this one, if there's only 2 ligands on it and they're changing positions, that's a good hint that it's probably cis and trans. All right, D, the only thing that's changing here is our ambidentate ligand. So we haven't talked about what ambidentate means. We've briefly mentioned it. It's like bidentate, but instead it has 2 bonding locations, but it only can bond through 1 at a time. So SCN is one of these things that has 2 binding locations. It either can bind through our sulfur, like we see in this case, or through our nitrogen, like we see in this case. So since we're changing how it's bound, what do you think it's going to be? Yeah, the linkage isomer. So this is...
Question about this. It's like not about like the exam.
Yeah.
Like I know you won't need to know it, but if you had like each of these things in solution, would like some of them go one way and some of them go another?
Yes.
How would you then like separate them?
So it depends. Sometimes you'll get multiple products, but like say this palladium complex, you're most likely going to get this top complex because palladium prefers to bind to sulfur than nitrogen. Typically, if we're trying to figure out what we have in solution, IR is a really good way because our metal ligand bond will change its shifting. So like for thiocyanate in particular, in the palladium sulfur one, I believe it shifts to a higher wave number. And then for palladium nitrogen, it shifts to a lower wave number. So there's a lot of different ways to tell this. And that's also why we call them like optical and geometric isomers, because like the optical ones we can tell by chirality, and that is directly linked to spectroscopy. Alrighty. So for the next one, we have these propeller type things. What do you think this is going to be? Any guess? There's only 2 answers.
I said this one's optical.
It is optical. So yeah, these are delta, and I actually don't know the name of this symbol. You don't need to know these symbols, but that's what they stand for. It's just right wing versus left wing. So when we see these types of propellers, it's a good hint that this is an optical isomer. Then for the last one, again, I highlighted the ones that we need to pay attention to. It's kind of obvious what it has to be, but when we have 3 ligands that are on the same equatorial axis, then it's our face and mer isomerizations. And then we have 3 ligands over here. So in one of them, we form this type of triangle down here, and the other one, they're planar. And these are another type of geometric isomer, but these are face and mer isomers. So cis and trans involve 2 ligands being opposite or cis to each other, and then face and mer require 3 ligands of the same type. So that's how you can tell your geometric isomers apart.
Would we be expected to, like, if we were given something, to, like, just know the name of it, or would we be given a word name? Does that make sense?
I don't know. I don't want to say definitively, like, we would expect you to know the name. For things like cis, trans, face, mer, yeah, I think I would expect. But as far as like linkage, coordination, and optical, I think those ones are a bit harder. Optical might be easier because it's just the delta and our other triangle-looking thing. But I would say this is a good representation of like the knowledge we expect you to know.
Okay.
But yeah, I can't imagine us saying like draw a geometric isomer and then just having you draw a geometric isomer.
It's really good blank code exams sometimes. So I'm like, oh, I know what this is, but I can't think of the name.
It's gonna be okay. It's gonna be okay. So next we have the catalytic cycle for palladium catalyzed cross-coupling carbons. So they just give us a cycle and they want us to name each process. So even if we don't know what all these names mean, we can figure out what's going on just by looking at our starting material and the product in each step. So in our starting material, what we have is this LNPD, so it's a zero valence palladium, and we're adding Rx to it. And what we see is both R and X get added to it. So what type of reaction do you think this is? We're adding two things to it. Yeah, oxidative addition. So oxidative addition, a big sign of it is we're increasing the coordination number by 2. We're adding 2 brand new things to our metal center. LN, where? Oh, that's just saying like it can be any number of ligands because palladium is zero valent. So oftentimes palladium catalyzed cross coupling is occurring with like nanoparticles and nanospecies, which are have your palladium core in its zero valent state. So the number of ligands it has isn't really known because we don't understand nanoparticle systems as well as we do molecular and organic systems. So this is just to show like it could be any number of ligands, but what we're getting out of it is this tetrahedral compound. All right. For the second step, what we see is our R and X ligand switch positions. Well, really our L and X ligand, these two ligands right here. So we haven't added anything. We haven't really changed anything. All we did was move 2 ligands that were already bound. So what do you think this has to be? Yeah. This is our cis-trans isomerization. Then for the third step, we're adding a singular ligand in, so it's some type of ligand substitution. But we need to figure out what type of ligand substitution it is because we have 2 different types listed here. We have trans and orthometallation. Orthometallation. Sure? Is that how you say it? So here is the ortho part of our ligand attaching to it. Does it have an ortho part? Is this a ring? No, so it can't be that one. It has to be the transmetallation. Another good hint is it's going trans to our other added ligand. Our 2 R groups are trans to each other.
So orthometallation needs a ring.
Yeah, so that's the one where we had like the ring was already bound to our metal center. I'll draw that.
And you're moving the double bonds in the ring.
Yeah, so and then we're binding this side to it as well.
Okay.
Yeah, so if you had something like this and then the next step was, I don't know if I can draw this very well. I don't know if I can draw that. This would go there.
Oh, okay.
And then we'd have 2 sides of our ring bound to our metal from the ortho position. Does that make sense?
Yeah.
So you typically need a ring for this to occur.
So metallation means substitution?
Yeah, so here we're using metallation because we're inputting a different metal complex. So this M doesn't stand for palladium. This is a different metal complex. I think often they use tungsten. I might be wrong on that. Maybe molybdenum. They add it, and then a ligand substitution occurs where our X ligand gets replaced onto that metal complex, and this R ligand goes here.
Okay, that makes sense. Sorry, I missed this lecture.
No, it's fine. I tried to record it, but it broke my surface.
So for the ortho one, are you starting with a ring and adding?
So yeah, you're starting with your ring already bound to it, and then your ring's ortho position is also getting bound to it.
Okay, so it's not like it's adding a ring. You're
Yes. Yeah, you're adding a ligand to it from your ring.
Okay, so the M and that would connect, is that what you mean?
Yeah, so like, I can't draw it very well. So I'll try just a different way. So say this is already bound to our ligand, right?
Yeah.
Now this is also going to bind to our
Okay, that
ligand
makes sense.
because that's the ortho position of it.
And it would replace something else.
Yes, so in this case, it would take off like our X group here. But I think we only talked about that in cases of like activating hydrocarbons. So if you see an activation of a hydrocarbon, that might be a step. All right, now going from R3 to 4, what we see is this R group right here goes over here, so it switches places with our L group. We're not adding any other ligands, we're just moving ligands already bound on it. So what do we think this is? Yeah. And this occurs because in the next step, it is reductive elimination. For reductive elimination to take place, we need our two ligands to be cis to each other. So if these two ligands are leaving and we're doing reductive elimination, they need to be on the same side. So this is reductive elimination, because we are removing two things and going back to a thing that is less coordinated. Any questions on that? And then, yeah, if you're thinking about like the other steps, like alkyl migration or what's the other one? Hydride migration. It's quite literally if it's already bound to the metal and we're just moving the hydrogen, or if it's already bound to the metal and we're moving the alkyl. That's what that means. It's not that we're adding an alkyl in or we're adding a hydrogen in. We're moving a hydrogen that's already bound.
What is migratory insertion?
Migratory insertion, it's insertion, but it's 1-2 insertion. So like say I had a double bond, I'm inserting at the 1 and 2 positions. Sorry, 1 and 2. Like that.
So how is migration different from isomerization?
Migration, it's because we're actually moving the ligand, like part of the ligand. So
So part of it staying bound, but another part on so if like this is the metal, this is the ligand, like half of it will move.
sometimes if it's just a hydrogen, what we'll see is that the hydrogen moves and another hydrogen gets placed there from what the hydrogen is added to, because oftentimes we'll see that happen when we're reducing an alkene to an alkane. So like we'll have our metal, it'll be bound to an alkene,
Yeah.
and then we'll see a hydrogen migration where we'll go to, now we have a hydrogen here, part of our alkane, and then the hydrogen that was originally bound to our alkane is now there.
That makes sense. Okay, thank you.
Any other questions on this one? All right. Here they give us 4 different MO diagrams, and they want us to classify water as a Lewis base, a Lewis acid, oxidizing agent, or reducing agent. I also provided the formulas, so you don't just have to look at the MO diagrams because they don't really illustrate the large energy differences that explicitly. So this is really asking, is the difference in energy between our frontier orbitals, so our orbitals that are going to interact with each other, is it large enough that they are not going to form an adduct, or is it small enough that they will form an adduct? And if it's forming an adduct, that is a good sign that we're doing a Lewis acid-based reaction. So starting off with the easier ones, we can do the Lewis acids and bases. If we look at this top example right here, we see Mg2 plus water forms this adduct. So this is a good hint that it's going to be either a Lewis acid or a Lewis base. So if I was looking at my reactants, what would you classify Mg2 plus as?
Like acid or base.
Yeah, acid or base, sorry.
It's an acid.
Yeah, it's a Lewis acid. So that means our water is going to be the Lewis base in this case. We know it's a Lewis acid because it is a metal cation. Metal cations can accept lone pairs. Oxygen or water can donate lone pairs. So part of this reason is because we can see Mg2 plus is low in energy. So Mg2 plus is low in energy. Is low in energy. So our water here can act as a donor. This allows water to act as a donor. So we can form orbitals or molecular orbitals that are stabilized lower in energy, and we form an adduct. So allows formation of stabilized orbitals. So this is in part due to we have a small energy gap, so a small delta E. So in the second example, right below it, we have our chlorine ion, and again, we're forming another adduct, right? We're going from two things to one, so they're bonding together. So this is also a case where it's going to be a Lewis acid reaction. Lewis acid base reaction. So since the first one was a Lewis base, this is kind of obviously a Lewis acid. And here we can also justify it if we look at our chlorine. Our chlorine is negatively charged. It has a lone pair that it can donate as a Lewis base. Our water has a orbital where it can accept a lone pair. It's LUMO, right? So we're going to form two lower energy orbitals, and then this helps us form our adduct. So similarly, here the orbitals are similar in shape and energy. So that's really the big thing here. We need orbitals similar in shape and energy for an adduct to form. So think of like NH3 and BH3. Those form adducts because NH3 is a good Lewis base, BH3 is a good Lewis acid. Same concept here. So here what we see is the lone pair of our Cl- is our donor, while H2O is the acceptor. Now if we go over to the left, what we can see is we have a little bit more complicated reactions. We're not forming one thing, we're forming multiple things. So this is a good sign that some redox chemistry is happening. The first thing that we can see is in the top left example, water goes to OH minus and H2. So H2 has an oxidation state of 0. So what we're seeing is water is getting reduced, right? We're going from a positive 1 oxidation state in our hydrogen over here to a 0 oxidation state in our hydrogen in our products. So we can clearly see water is getting reduced. So here it is the oxidizing agent. In hydroxide, it's still +1, yes, but in H2, it's 0 because that's the elemental form of hydrogen. Yeah, so O2, N2, those are all 0 because they're elemental forms. Metals are 0 in their elemental form, so our calcium then, what we can see is 0 on our reactant side and then +2 on our product side, so our calcium is getting oxidized. So here, H2 is reduced to OH minus, well, technically to H2, OH minus isn't technically reduced, it's the same oxidation state, to H2. Additionally, there's a large energy gap between our frontier orbitals. Between frontier orbitals. So no adduct can form. And here, large delta E. And then that means our last example kind of has to be our reducing agent. So if we look at this one, what we can see is we're going from O2 or H2O, which has a -2 on our oxygen, to O2, which is 0. So we're increasing the oxidation state. Our H2O is getting oxidized. Bless you. And then F2 is going from 0 to -1, so fluorine is getting reduced. So the F2 frontier orbitals, these orbitals over here, F2 frontier orbitals, are low in energy. And there is a large energy gap. So instead, what we see is complete electron transfer. So here the MO diagrams are here to kind of help you reason out what the reactions are telling you and then use them to support your answer. So a big supporting factor here is if we have orbitals that are close in energy, we can form an adduct. If we have orbitals far away in energy, they don't form an adduct. We instead see complete electron transfer. But depending on if it's higher or lower in energy to our water, that depends if it's oxidizing or reducing, or is it a Lewis base or a Lewis acid. Make sense? Yeah.
So, is there any like rules for us to be able to do this without the molecular diagrams, or do we need to know those energy differences to be able to do this?
If you understand why electron transfer is occurring, then you can reason it without your MO diagrams. You would just say electron transfer is occurring because there's a large energy difference between our orbitals. And then you would have like the formula to support your answer. So you could reason it without it. I think it's easier to reason it with it.
Yeah. I'm just like, will we ever be asked like if you have water and calcium, like will it like do a redox reaction or will it form an adduct?
I would say these examples are fair game because they were in the lecture slides as well. So I know when I took inorganic chemistry, I had to show water as like an extreme acid and extreme base as an oxidizing and reducing agent, and that was my question. It wasn't like there was no formulas, there was nothing. I had to draw the MO diagrams. I don't think we would give it to that extent, but if we asked like provide an example in which water is acting as an oxidizing agent, I think that's one that you can do. And similarly, your orbitals don't need to be perfect, but we should understand that if it's an oxidizing agent, electron transfer is occurring, large delta E. And that means that our ligand, whatever else that we're working with has to be higher in energy than our water. If it's reducing agent, it's going to be lower in energy than our water.
Is there a way to predict that? Like if like you're just like, oh, calcium, like how do we know that it's so much larger? Is there like
just for these ones, I would say know these ones, but I wouldn't say like
so
I wouldn't know if like someone gave me magnesium versus calcium, how I would know the difference between those two rather than just like
okay,
I'd have to look at it.
Like, because sometimes we're often given like here's trends, so
Yes.
there's not trends to describe this. This is just what
There might be. I just don't
we
know
just
them.
don't know.
Yeah.
Okay.
Yeah, I think it's more important we understand water can do all these things and
Yeah.
why it does all these things, but
We don't have to predict.
yeah, just be able to explain it.
Lewis asked the small change too, right?
Yes, so Lewis acid, Lewis base, small delta E. So that's why they can form an adduct because they're so close in energy to each other and they have similar orbital shapes. Alrighty, we did a problem like this today. So here they give us 3 strong acids and they ask us to determine which one's the strongest in water. So if you're ever given a problem like this, the first thing I suggest is write out the reactions in water. And you'll see very clearly why I'm going to say this in 1 second. Can anyone guess what the third one's going to be? Same thing, just different anion. So based off this information, which one do you think is the strongest in water? They're all the same, that's exactly right. So all of them are equally strong in water. Do you know why?
They're all strong acids. So
Yes, but specifically in water. We talked about the discrimination effect earlier today. What's the opposite of the discrimination effect? The solvent leveling effect. So when we have all 3 of these acids in water, they all produce the same acid, H3O+, which is the strongest acid that can exist within our solvent leveling window of water. So anytime we put a strong acid in water within a certain window, it has to be H3O plus, the strongest species in water. However, if we put it in another acid, we can discriminate we can decide between the three because of the discrimination effect. Now they're all going to have different strengths in acid. If we put them all in base, they're all strong acids in base and are going to completely neutralize. So here, they're all equally strong in H2O due to the solvent leveling effect. So they all produced H3O plus. Which is the strongest ion in solution. Any questions on that one? That one's just kind of like a vocab problem, really. All right, our favorite, Latimer diagram. Latimer, I think is how you say it, right? Latimer diagrams. These are electrochemistry. So for the first one, they want us to write the reduction of CuO2 plus to Cu solid in acid. So we don't have to worry about adding OH minus. We're just going to balance out our equation. So starting off with the very basic, we know we're going from CO2 plus, not CO2 plus. It's 2 plus up top. To Cu solid. So when we start balancing redox reactions, always going to be the same thing. First balance of things that aren't oxygen and water. We have the same amount of coppers. We don't need to do anything there. Next, we're going to balance the oxygens. So to balance oxygens in a redox reaction, you add water. So since I only have one oxygen, I'm going to add one water. But now that I added water, I have some hydrogens that I need to balance out. So that's the third step. You're going to add hydrogens. So I'm going to add 2H plus over here to balance out my hydrogens. And then the last step is balancing the charges. So if my product side has a charge of 0, right, water is neutral, copper solid is neutral. My reactant side has a charge of 4 plus, because I have 2 H pluses and then a 2 plus from my copper oxide. So I need that to go to 0. So I'm going to add 4 electrons to balance out my charge. And that's my balanced reaction. So if I look for my H plus coefficient, H plus is 2. If I look for my electron coefficient, it's 4. The next one, they want us, any questions on balancing redox reactions? Same steps every single time you do it. Balance things that aren't oxygen and water, balance oxygen, balance water, balance charge. Always do it in that order. If you don't, it gets a little messy. So now they want us to calculate the E cell for the reduction. So since we're doing reduction, we don't need to change any numbers. If we were doing oxidation, so going the other way, we need to flip the sign. But here, we're going left to right, we keep it the same. So this is the formula where you do N times your energy, N times your voltage. So what we'll do is our E is going to equal, that's a horrible line. I can't draw a line. So first we're gonna start off with our CuO2 plus to Cu2 plus. How many electrons are being transferred here? What's the change in oxidation state? 2, so we have 2 instead of 1 times our difference, which is that positive 1.76 volts. Then we add that to the next transfer, so from copper 2 plus to copper plus, that's only a 1 electron difference. So it's 1 now times its volts. And then copper plus to copper 0, that's also a transfer of 1 electron. So 1 times 0.520 volts. And then I'm going to put this all over however many electrons I transferred in total, and that's at 4 electrons. Or you could just add up your numbers here, 2 plus 1 plus 1. So 4. Doing this math, I get a voltage of 1.5 volts. Sorry, voltage? Yeah, no, that is voltage. then if you forget this formula, it is on your data sheet, but it's not explicitly on your data sheet. So if we go down, it's right here. This is the formula that we're technically using, but it's not explicitly drawn out the way that we went in class. This is it, like, in its very bare bones. So what we're doing is the summation of our energies. We can get rid of F because we're doing the summation of it, and our F's cancel out. But if you do forget how to calculate it, just take a second and look at that formula, and it's just any plus any plus any over n. All right. Now Frost diagrams. So Frost diagrams go hand in hand with Latimer diagrams. They just plot the same information. Here, they want to know which ones are thermodynamically stable to respect to disproportionation in acid. So disproportionation is the spontaneous oxidation and reduction of a species. So oftentimes we talk about this with H2O2 because we can get O2, H2, and O2, H2O? I don't know. H2O2 typically does disproportionation reactions, so oxidized and reduced at the same time. Here, what we need to figure out which ones aren't going to spontaneously disproportionate. So if we remember from class when we drew lines connecting things, things above the line are unstable. So those disproportionate. And that makes sense. When we think of copper, we don't think of copper in the +1 oxidation state very often, right? It's usually in +2 or solid. So it makes sense that copper plus isn't a very stable species. We're looking for all the stable species. The only thing above the line here then is going to be our copper plus. So all three of these fall under stable. So if it asks for unstable, the answer would just be copper plus, because it's above the line.
So wait, what do you draw two lines between? Because
Whichever species you can. So like I could draw two lines between these two, but there's nothing above it. Nothing's going to happen. I could draw two lines between these two, but nothing's above it. Two lines between these two. It's just between two of the species on your graph. And then if anything's above that line, that means it's unstable. So here, I'm drawing it between copper 2 plus and copper plus is above that line. So that is unstable.
So if it's unstable,
It will disproportionate.
it will disproportionate.
Yes.
But if it's stable,
It won't, yes.
so CuO2 plus, and why is that stable?
'Cause it
technically
can't-
that line, so if it's not like above or below the line, it's also stable.
Yeah, so
Okay.
this one's the highest one, so it can't disproportionate in both directions. It can reduce, technically, right? Because this is -2, so that's +4. Yeah, this would be a +4 oxidation state. So I can reduce it to copper 2 plus, but I can't further oxidize this.
So your line's gonna want to have something above it as well.
Exactly.
Okay,
Yeah. Any questions on that one? Cool. All right, our favorite type of problem. MO. MO. So here, I didn't include the relative energies. I probably have them listed somewhere, but I try to draw them as close to each other as I could to represent like what's interacting. I think the best way to go about these problems is just think about them real quick. If we have a 2H atoms and a carbon, we already know that our s orbital, our 1s orbital, isn't going to interact with it, right? Like, that isn't our principal quantum number. Our 1s orbital is a non-bonding orbital. It's just included in there just to be there. So that's where I'm going to start off with, is just drawing this one, because we know this is non-bonding. It can't interact with anything. It's too low in energy. So now we're going to look at our 2s and our 1s of our hydrogens and our carbon. So in my 2s orbital, I can have different configurations. If I have my two hydrogens in phase, they're all the same thing, right? So that's going to be a really low energy scenario when they're all in phase. So we're going to have another orbital right down here. It should be a little bit lower than our 2s orbital because we're stabilizing that. I also can have another scenario where my carbon is out of phase with my hydrogens, and this creates two nodes. So this is going to be a higher energy orbital because we're destabilized now. So we can draw a higher one up here. Now that's taking care of our 2s and our 1s interaction. Now we need to look at our 2p and our 1s interaction. Now which p orbital is going to interact with my s orbital? My pz, my px, or my py? pz. So that tells us that we know two of our orbitals then in our p are additionally non-bonding. Our px and our py do not interact with our s orbital because they're not on the same axes. So if we're looking at my px, we could just draw it like this because it doesn't matter. It doesn't matter what phase they are, they're non-bonding, they're not interacting. If we're looking at the other scenario, same thing. They're non-bonding. It doesn't matter what phases our hydrogens are in, so we can just draw them as dots. So now we're just down to 2 more orbitals that we need to place. How is our pz going to interact with our 1s? So again, we can go down here. I'll draw my pz. So if I have them, sorry, that was a bad one. There we go. If I have both my things out of phase, so I have one dark here, and then one light here, this is a pretty favorable interaction, right? They're all stabilized. It's not as stable as this one, so it'll go slightly above it. It's gonna go below our 2p, below our 1s, because it's stabilizing both my 2p and my 1s, but my 2s is much more stable than my 2p. So it's gonna go above that. And that means I also have one other scenario for my orbital, which is they're out of phase. Now this is much more destabilized than this scenario because what we're seeing is if I drew this more accurately, it would be like it squishes these orbitals in the middle and it forms like this really ugly type of structure where everything's kind of squished together and really doesn't want to be there. There's a lot of repulsions going on. So what we get is a higher energy orbital right up here. Now we're just going to draw the lines connecting our orbitals to what they stand for. So our 2s, we know, contributes to this lower energy orbital and this higher energy orbital up here. And same thing with our 1s, because those are the ones contributing to them. So this orbital is 1, 2, and 3. And then this orbital up here is 1, 2, with 2 different nodes in it. And since these are interactions between our s orbitals, we know they're sigma. So this would be our regular sigma. And then this would be our sigma star up here. Now going down to my p orbitals, I know my 2p is interacting with this orbital, as is my 1s, and that's going to represent this interaction here. And then I also have a higher energy orbital that represents the anti-bonding interaction. And this one also has 2 nodes. And then the last thing we need to do is, I should write what these orbitals are then. So down here, this is going to be a sigma non-bonding orbital. Here we have a sigma bonding orbital, another sigma bonding orbital. These are pi non-bonding, and then these are both sigma star.
So they have 2 different sigma.
So yeah, if you remember, there was a problem a while ago where we were labeling electron configuration a little, actually I think it might have been on your homework, where it asked you to do the electron configuration. So if I'm talking about my 1s, it would be like 1 sigma, and then when I go to my 2s, 2 sigma, my 2p, 3 sigma, when I'm like listing it out, and that's how we differentiate between the 3.
So on the other practice exam, it was a very similar question. They also had the 2p connect to the sigma g, like the first one. And when we were at office hours yesterday, they were kind of confused
So
on that too.
for that one, what they did was the sigma g, they didn't include the 2s in it. Are you talking about the practice exam or the practice exam? I haven't seen that.
Yeah.
Let me look it up after we
Sorry.
go through this, and then we can talk
Yeah,
about that one.
I did office yesterday. I didn't understand why it went to Sigma G as well.
Yeah,
It's
I haven't
really weird. It's like the
seen that
exact
one.
same setup.
Is it the beryllium one?
Yeah.
I might have that written down.
That's okay. We can look at it later. I'm just wondering if there's a reason. If it is always gonna look like that.
So they all look very similar because our 2pz is the only one that's going to interact. As far as like bonding with your 2s or your 3s orbital, like the one that we did in class today, I asked Dr. Lori if we would take off points if you had connected your 3s orbital, because we technically we had the same thing illustrated, but our 3s orbital wasn't connected. Yeah. And she said it's okay either way. So it's because there's not like definitive rules for the energy differences that you need between orbitals for them to interact, but there is some type of interaction. So if you draw the bonding orbital, then you should be drawing.
Do we have to say whether it's U or G?
Does it tell you to say whether it's U or G? I don't know. It does not say whether it's U or G. So I would say no unless it explicitly says through two, because here it just says clearly indicate which molecular orbitals are sigma, pi, bonding, and antibonding and non-bonding. So sigma, we did that. Pi, we did that. Non-bonding, bonding, and antibonding, we all did that.
If we had to, wouldn't it go like GU and then GU?
Yeah. Same order, but that's just extra information. I think she pulled the example today from a textbook, which is why it was so detailed. But I think this is fine enough for what we're doing here. Because, those aren't the non-bonding. These are the non-bonding here.
Yeah.
There are no notes. Those are our hydrogen orbitals, or hydrogen ones, hydrogen.
So just to illustrate that they're there.
Yeah, like it doesn't matter what phase they're in. They can be either in phase or out of phase, and it's not changing it because they're non-bonding.
Gotcha.
So that's how you illustrate something if it doesn't matter.
Okay.
All right, so now the last step is we just need to fill in our electrons. So if we have carbon is a not D6. It's not a metal. It has 6 valence electrons. Technically 4, but including our 1s. So 1, 2. And then since this is H2, we'll have 2 electrons over here. And now we're just going to fill them in like we usually would. 1, 2, 3, 4, 5, 6, and then 7 and 8. And the last part of it, it asked us for the bond order. So before we do anything, what do we know about methylene? What should the bond order be? What is methylene? It's double bonded carbon. So yeah, methylene is a double bonded carbon. So this tells us that whatever our bond order should be, we should get 2. If we're not getting 2, we've probably done something wrong. So bond order, we're just going to look at our bonding and antibonding orbitals. So here we have 2, 4 in our bonding, and there's nothing in our antibonding orbitals. So we would do 4 minus 0 divided by 2. Wow, we got a bond order of 2. That's wild. So yeah, we're only grabbing these electrons because these are our bonding electrons. We don't care about the non-bonding electrons, and there's nothing in our antibonding orbitals. Yeah.
So how does this then translate if we're only thinking about the bonds with hydrogens?
Well, we have 2 bonds to our hydrogen.
So where's the double bond?
We just have 2 bonds is what it's saying. So typically when we think about methylene, it is double bonded to something. In this case, we're just looking at our CHC or HCH. So it's the 2 hydrogen bonds to our carbon. Does that make sense? I try to reason things out with like logic. So I had a similar problem when I took my class, but we had to do like draw basis sets and like how the actual orbitals are influenced once they're bonding and antibonding. So like instead of this orbital, I had to draw this, and that was the orbital that I had to provide because that's really the shape it would be. But you guys don't need to do that. In this case, the reasoning here would be, we know it's bonded to 2 things. We should have a double bond or something of 2. Any questions on this one? All right. More electrochemistry. So this one is just asking us to shade the region where FTO3 is stable in liquid water. So all we need to know then is between these two blue lines is where things are stable in water. We're looking at this species right here, which encompasses this whole block. And we just want to highlight where is it stable in water. So anything below this line and to here. This is our stable in water area. So it has to be between the two blue lines and just encompassing our F2O3 region. So it doesn't include this little region down here because that isn't F2O3, that's F3O4. Just this region right there that's colored. I'm gonna get rid of that outside though. So anytime we're asking about water on the Pourbaix diagrams, just between the two lines, two blue lines. Or I guess diagonal lines, yeah. All right, let's talk about some kinetics. Any questions on that one? That one was a pretty mundane one.
I hope they're all like I hope it's like, I hope there's that question.
I'm not good with those diagrams.
Give me 4 points for that.
So,
You just gotta color something.
looking at those diagrams, is the main thing we should know is like the dotted lines is like where it's reacting with water.
Yes. So same thing, like just understand how to read them. So if we're going across one of these lines, that means we're doing a redox reaction, right? And then the lines mean other things, but I don't think you necessarily need to know exactly what the lines mean. So some of them are redox chemistry, some of them are not redox chemistry. But for the main part, it'll be really explicit what we're asking you, and you'll have seen the question like before, like to some extent. It's not going to be like a random question, like where is the passivation and corrosion of iron stable in this graph? Like I wouldn't ask you that because I don't think you guys would know what that means in a sense of a graph like this. Kind of. It's a little bit more complicated than that, and this isn't the full Pourbaix diagram for iron. Well, it is, but it's illustrated a bit funky. It's several regions. But yeah, like the one that we asked you today in class, I think that one's a fair one because it's just we're going from H2O to O2. And that's just how do I get H2O to O2? Even without the reactions on the line, you can figure it out because you would just balance the redox reaction between these two.
Could you also just look at it like O2 is going to be produced?
Yeah.
So whichever.
Yeah.
Could you just like make an equation, or would you have to use like the diagram? That makes sense.
So you would need the diagram to a certain extent because we need to know what conditions we're at.
Okay.
So it changes depending on the voltage. Here, it's not really asking about the voltage. Another good type of question is like, what voltage and pH would this be stable at in water? But like, I don't think we're gonna ask you anything like beyond the scope of what you've already seen. Alrighty. They want us to calculate CFSEs of complexes. They're both chromium. Does water have any charge on it? Nah, so we have chromium 3+, and then we also have chromium 2+. So chromium 3+, what d electron count is it? D3, yeah. And then that means chromium 2+ is D4. So since we have a D3, we don't really need to think about high spin versus low spin. It only can be one thing, right? So 1, 2, 3. And if I was to calculate my CFSE for this, how would I do it? Do you guys get that equation up here? I don't see it on here, so know the equation. Yeah. I do 0.4 and 0.6 just because I prefer decimals, but 2/5, 3/5 works also. So here we would do 2/5 times, 2/5 delta O times 3 because we have 3 electrons. So that gives us a 1.2 delta O. Or how do I? Sure, if that's the same thing, 6/5 delta O. So what we see is we have a pretty large CFSE for this one. And then, ooh, what did I just do? I didn't like that. All right, here we go. Oh, here we go. Awesome. So then for our chromium D4, is this going to be high spin or low spin? Yeah, high spin. Water is a weak field ligand, so high spin. So here then, our math's a little bit different then. We would do, again, 3 times our 2 over 5 delta O. But now we're going to subtract out our 1 times 3 over 5 delta O. And this gives us a 0.6 delta O. So we can see one has a relatively large crystal field stabilization energy. Technically ligand field stabilization energy, but I think we use them interchangeably in this class. So crystal field stabilization energy, and one has a relatively high. So based off this information, what do we imagine Cr3 plus to be, inert or labile? Is it more or less stable? Yeah, it's inert. So again, if we remember some of these trends, if we have a large CFSE, that typically corresponds to a kinetically inert compound because they have a high activation energy. They're very stable because we have this half-filled subshell down here. And then what do we imagine Cr2 plus is then? Labile, yeah. So these ones are easier to react. Well, not easier to react. They react faster because we have a lower activation energy and a lower CFSE. So this problem is about connecting trends between CFSE and kinetic inertness versus lability. Lability? Lability. I think that's how you say it. Any questions on that one? No?
We have to explain why. Or could you say like because it's a large CFSE?
I would say try to hit large CFSE, the activation energy, the reaction time, right?
So large CFSE, what's that mean? I guess
Large
like activation.
So large CFSE means that we're going to have a larger activation energy and we're going to have a slower reaction. Welcome, guys. How are you doing today?
We're doing great.
Oh, I hope your physics exam went well.
Haven't taken it yet.
Oh, Hannah, what's up?
Sorry, I didn't know. Is inert when it has a low CFSE?
Inert is when it has a large CFSE because it's more stable.
Why should we talk about pairing energy? Only
So-
like when asked, or do we normally include that when talking about CFSE?
So here, pairing energy doesn't play a role in it because none of our electrons are paired, but we'll see it in actually the next problem. So yeah, I asked these 2 types of problems back to back because I thought it would be a good like matchup to understand. And like certain situations, we do need to talk about pairing energy, and sometimes we'll say in the problem itself, don't regard the pairing energy. I believe we did that last year on the final. I can't guarantee that's always going to be the case. So read the problem. If it doesn't say not to include pairing energy, include it if you have paired electrons. So I guess on that note, we can move on to 8 then and talk about what it means to have pairing energy included in our CFSE. So here, I gave you the name of it. I tried to choose something that wasn't very, very complicated, something that didn't have a bunch of like weird things going on, because inorganic naming and IUPAC naming can get very complicated, and it all depends on what type of chemist you talk to for how they want to name things. So I thought this one was really straightforward. We should be able to look at basic inorganic compounds and figure out what they are based off the name, but you don't need to know how to name compounds. Does that make sense? So here, it says hexa, so that tells us 6. Cyano tells us Cn minus. Ferrate tells us iron. This 2 tells us it's in the +2 oxidation state.
Is it for the iron is in the +2?
Yes.
Okay.
Yeah, so typically inorganic naming conventions, sometimes they don't include oxidation states. Here, if I'm writing it, I will include the oxidation state, and it'll always be in the parentheses. So that's just telling us we already know iron's in the +2 oxidation state. Yes.
Is 6 for the cyan?
Yes, that tells us how many ligands we have. So here we have an octahedral cyano iron complex that is in the Fe2+. So like if I wanted to draw that, it would just be Cn, 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 and Cn, just like that. Yes?
Do you think that there are some like compounds that we should avoid?
Yes. So as far as like ligands go, we should know the charges of like cyano, -1, because we have 11 electrons, or carbon is what's negatively charged in our cyanide complex. Technically, you have cyanide and isocyanide, but when we're talking about metal complexes, we're just going to say cyanide for the case of this. So yeah, our carbon is the one connecting to our metal. Carbon monoxide, that's neutral, because our carbon is negatively charged, our oxygen is positively charged. Cancels out. Hydroxide, -1. Ethylene diamine, neutral. EDTA, -4. Stuff like that. Is it really?
Well, it's
Oh, yeah.
a series, but it shows the.
So, yeah. It does. You have these, but remember, these also don't tell you what are strong versus weak. So when we're looking at them, things down here, these are our strong field ligands. Things up here are our weak field ligands. Though I-, that's strange. Interesting. No, that's fine. That's actually fine. So yeah, they don't tell you what they are, but they do provide a list. So if you don't necessarily remember the charges, just come back here real quick. All right, so now that we talked a little bit about this, we know iron is in its 2+ configuration. So what d electron count is that? Yeah, d6. So the next question I have is this going to be high spin or low spin? Yeah, it's low spin. And why is it low spin? Circled why it's low spin.
Why is it D6?
It's d6 because we have iron in the 2+, so we're going to remove the 4s2 electrons, and that just remains our d6 electrons, or 3d6 electrons. So yeah, because we have cyanide, it is a strong field ligand. It can pi back bond. It is a sigma donor and a pi acceptor. It's going to be a low spin system because we have a large delta O, right? It's really hard to promote the electron rather than pair it. So that means everything's going to be down here. So in this case, how do I calculate my CFSE? What do I multiply by my 2/5? What was that? Because it's low spin.
I thought you said it has large delta O, that's why it's low spin.
So I think they play hand in hand. It has to be low spin because the delta O, the difference between our T2G and EG, is so large that it's harder to promote an electron than it is to pair an electron.
How do you know it's low spin?
Because we have cyanide, and cyanide is a strong field ligand. Oh, I'm so sorry. I kind of went a roundabout way of answering that. My bad. So yeah, since everything's in our T2G orbitals, we do 6. But we have things paired up, so we need to take into account the pairing energy. So this is 2.4 delta O. So we're going to look at all our degenerate electrons, or degenerate orbitals, and just place them in like we usually would, with 6 electrons. And what we realize is when they're all degenerate, we only have one thing paired, but in low spin, we have 3 things paired. So we would have to do minus 2p because we have 2 extra electrons paired up.
So it takes away from that.
Yes.
So it's like whatever it is, it's
Mm-hmm. Because it takes energy to pair up electrons.
because in class she had them both the same sign, so
I don't think we would minus off points because also with CFSE, some people do it negative versus positive. Like I learned it opposite. I learned it negative, but as long as you're consistent with it, since we're doing positive in this class, we'll do positive.
So pairing energy will always be opposite sign.
Yeah.
The CFS.
Exactly.
Well, you never really add pairing energy.
What?
You never really.
If you did it the opposite way, then you would have to add pairing energy because then you would have a negative number. But in this case, we're doing positive, so we can minus it out. But I don't think we'd like explicitly take off like a lot of points if you like switched up the sign of your 2p or pairing energy. Does this problem make sense? Cool. So now it's going to ask us some questions about it. So we already answered these questions, but I put them afterwards so people would first think about how to answer this and then go back and be like, oh, wait a minute. So here we said it's low spin. And we know it's low spin because we have Cn minus. This is a strong field ligand. that participates in what type of bonding is, yeah. How do I spell participates? I don't know if I spelled that right. That seems,
Yeah, that's good.
that is?
Yeah.
Oh, okay, that seems way wrong. Back bonding. The delta O, so energy between our two orbitals, or two degenerate sets of orbitals, is very large, making it energetically favorable. Favorable to pair up electrons rather than promote.
So when we're saying like low spin and we're talking about like really strong like our aerospace electrons and stuff like that, all that low spin means is that they're all going to pair up before they go to the high energy,
Exactly,
right?
yes.
So if they're high spin, it'd be like single one way longer before
Yes.
they pair up.
Yeah, so we would first go up in energy, fill up those two,
And
then go back down.
Okay.
So this really becomes an issue, like high spin versus low spin, from D4 through D7, right? 1, 2, 3, 4, 5, 6, 7, 8. D4 through D8 is when we really need to account for high spin and low spin, because D1 through D3 only can have one configuration. D9 through D10 can only, or D8 through D10 can only have one configuration. Doesn't matter if it's high spin or low spin. Like, there's only one way to fill in the electrons.
Because it's either, it has to be on flow or
Yeah,
you only have one metal.
exactly.
Okay, that makes sense.
For the spectrochemical series, like at the bottom, does that tell you like what's a strong ligand, what's a weak ligand?
Yeah, so
So where would the cutoff be between strong and weak? Does that make sense?
there's not a hard cutoff.
Okay.
So oftentimes we have things that are in the middle, like even when we're talking about transdirecting, like things over here are strong field ligands, but we can talk about NH3 and CL is a stronger field ligand than NH3, but it's not a strong field ligand.
Didn't we say H2O was like a weak field ligand?
Yeah, it's a weaker field ligand, but it's somewhere in the middle. Like it's weaker when compared to other strong field ligands.
Okay, so like if we have a problem like this, would it be like pretty straightforward if we're gonna know if it's like high spin or low spin based on like
Yeah, yeah.
It wouldn't be somewhere like kind of in the middle. It'd be like, oh, you can
Yeah.
assume. If that makes any sense.
The H, the NO, the CO, the CN, and the C2H4, those are all strong.
Say that again. H, NO, CO, CN, C2H4 are all strong fields.
Yeah.
They're all transdirecting, so they're all primarily strong field ligands, yes.
Aren't all transdirect?
No. So our weaker field ligands would be like our fluorine, our water, right?
So do the like the greater than less than, is that referring to strength?
Is the greater than?
There's like you see like the signs.
Oh yeah, so that's referring to like their impact. So for transdirecting ligands, that's saying the ones at the end are more transdirecting. And then for a spectrochemical series, this is saying that the ones at the end are more pi acceptors. The ones at the beginning are pi acceptors, and then the ones in the middle are sigma donors.
Would we expect an H3 to be like a strong field ligand?
No.
No.
NH3 is moderate, I would say.
Okay.
Yeah.
So is the main ones would be like CN and CO for strong field?
Yeah, so what I would say for like pi back bonding, a strong field, CN, CO, strong field, also phosphorus, NO2, yeah. Those ones are really.
Does NO2 do pi back bonding? Because I thought only CN and CO.
No, NO2 does not do pi
Okay,
back
so
bonding.
is CN and CO the only ones that do pi back bonding?
Yeah. That's why those two are up there.
So that's probably that'll probably be the main strong
Yeah.
field one.
The phosphorus does a different type of donation. I don't know the term off of the top of my head, but that's why it's also up there. It's that other one that has like multiple arrows pointing in and out. But I don't think that one's as important as pi back bonding. All right, so the next part is, again, it relates back to A, but now we're just breaking down the logic for how you did A. So is delta O. So delta O, remember, is just the spacing between our orbitals. For octahedral complexes, larger or smaller than the pairing energy. Well, if we're saying this is low spin, we're saying that it's easier to pair up an electron than promote the electron. So our pairing energy has to be smaller than our delta O. Delta O is larger than our pairing energy.
And does it have phones for
Yes, and then conversely, if we had a high spin, so I'll go over here, high spin, our delta O is smaller than our pairing energy, so that's why we promote an electron up, because it's easier to promote an electron up. Like, it's less energy to go up in energy. Or yeah.
Essentially, what you're saying that it requires less energy to pair because high spins have such high energy.
Exactly. So, like, if I had my low spin one, no, my high spin one. So this would be like my high spin one. It doesn't have a large gap. This would be my low spin one. It has a larger gap, so it's harder to bring up that electron.
So it's kind of like
We're like weighting the cost. Like pairing up an electron requires energy because there's repulsions of our electrons. Promoting an electron requires energy because we're moving it to a higher destabilized orbital. So we're just comparing those two things. Which one's easier to do? All right. Any questions on those? We're almost there. More MO diagrams. These ones are simpler. You don't need to draw like both sides. It just says the MO energy diagram. So quite literally, we just need to draw the MO. No atomic orbitals unless you really want them. You can include them, but that's all up to you. So since we have two things that are mixed together, our nitrogen and our oxygen, what do you think about our 2s, 2p mixing? Are we going to have sp mixing? When we have heteronuclear atoms, we have sp mixing. When we have things that are lower in energy, so let me pull out my periodic table. So we're thinking about our diatomics all the way up to nitrogen. So lithium, beryllium, boron, carbon, and nitrogen all have large 2s, 2p interactions. So we have our pi orbitals lower than our sigma orbitals. And then O, F, Ne, if these are all diatomic, these have our sigma orbitals are lower than our pi orbitals because they don't interact much. Our 2s and 2p don't have a lot of interactions. So since we have heteronuclear, we have a lot of sp mixing. So that's what we're going to regard when we're drawing our MO diagrams. So if we remember way back when, I'm going to include the 2s just to include it. I don't know why. I like to include them. So we would have our 2s over here. These would be our sigmas, our sigma 2s, and then this is our sigma 2s star. Then we're going to go to our 2p. So this is what I mean. These are lower in energy. Our 2p, pi 2p, is lower in energy than our sigma 2p. If we had O2, F2, and E2, these four orbitals look slightly different. They look like this, where our sigma 2p is lower in energy than our pi 2p because we don't have high sp mixing. So I'm just going to copy and paste this a couple times because we need it a few times. So now we're going to fill them in for each set. I'm going to start off with NO here in the middle, and then we're just going to branch out for both of them. So how many electrons does NO have for its 2s and 2p? If nitrogen has 5, how many does oxygen have? It has one more. 6, right? 5 plus 6 is 11 electrons. So we have 11 electrons, and we're just going to fill those in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Now if I have NO minus, that means I'm adding an electron. So I have 12 electrons now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then NO plus, I'm taking away an electron. So I have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's all this first part is asking for. Draw these diagrams, that's it. The second part wants us to calculate the bond orders. So we'll start off with our NO minus. Our bond order is going to be our bonding minus our antibonding divided by 2. So you can include your 2s, or you don't have to include it. It's all up to you. I'm going to include it since I drew in my 2s orbitals. So here I have 2, 4, 6, 8. 8 bonding electrons. And then in my antibonding, I have 2, 4. And then if I divide this by 2 then, I get a bond order of 2 for NO minus. Now if I go to NO regularly, I haven't changed the amount of bonding electrons I have, but I have increased the amount of I decreased the amount of antibonding, right? I got rid of this electron. I have 1 less in my antibonding orbital. So I have 8 minus 3 now. I'll divide that by 2, and this gives me a bond order of 2.5. And then for NO+, I've taken away another antibonding electron. So now I have 8 minus 2 over 2, and this gives me a bond order of 3. So NO, NO+. For part C, they want us to rank the molecules now by strongest to weakest bond. So how does that relate back to my bond order? What was that? I'm so sorry. Are you saying the largest bond order is the strongest bond? Yes, exactly. So the largest bond order means we have the strongest and shortest bond. So oftentimes bond order does correspond to the actual types of bond that we have. So I like to think of, if I have 3, that most likely means I have a triple bond. If I have 2, that most likely means I have a double bond. And if we're just thinking about a double bond versus a triple bond, we know triple bonds are much shorter, but also much more strong than double bonds. So if I had to rank this then, I would see that NO plus is going to be the strongest because it has a bond order of 3, then followed by NO because it has a bond order of 2.5, and lastly NO minus because it has a bond order of 2. So again, this is because the larger the bond order, the shorter and stronger the bond. Yes.
So would there be SP mixing if it was like CNN?
Yes.
So like other than like N2, C2, or like of the same molecule?
I would say most heteronuclear are going to have large 2s2p mixing.
Oh, wait. So if it was, oh yeah. If it was 2 like don't normally have SP mixing, so like O and
F maybe, then yeah, I would say it's probably more appropriate to do it that way, like the where it's not mixed.
okay.
Yeah.
Okay. But if it's like one from before the trend and then one from after, they're gonna do SP mixing.
For the most part, like heteronuclears have large 2s2p mixing just because the energies line up much better. But I don't think we'd give you any like heteronuclears that you wouldn't be expecting. Yes.
So when it, for the other part, when you said it didn't actually drop it to X, so it'd be perfectly fine if it has to remember orbital, which is straight with valence, or should we just have
I would say include the 2s, but including the 1s isn't really necessary. When you're calculating bond order, you don't really need to count the 2s because they're going to cancel out, right? We're doing 2 minus 2. So that you could have just done 6 minus 2, 6 minus 1, and then 6 minus 0.
what are the molecular orbitals that we're doing class there? I guess the difference in drug valence, like you have the atom side, the other side, and then the
So they're the same things, but these are for our main group elements. What we were looking at earlier is something that has more than one connection to it. So these are going to be combining 3 things, so we needed basis set, which is what we have over here. So this is just a more involved type of problem where we actually have to think about where the orbitals go now because we have 3 things rather than just 2 things. Yeah. I actually find this problem easier than the other problem, but that's probably because I just have a strong MO theory background. I feel like this problem you can easily not easily, more easily reason out than the other problem. Like the other problem, you just have to kind of know, like, this is how the orbitals are. Here, you're the one placing the orbitals, so it gives you the option to, like, well, I know these orbitals are here, so my MOs have to be somewhere in the middle, and we give you the shapes of the orbitals, so you just have to play around with things.
If it doesn't play energies, how do you know if they would
Here, I try to make it obvious by, like, including the 1s, so you would know that this one's non-bonding. I should have included the energies. I do have them. For the sake of this class, assume whatever the principal quantum number is, that s orbital is going to interact with our 1s. Again, I think you missed it. I was talking to Dr. Lori during class. That problem that we did during class with the same one, she didn't draw, or the image didn't have a 3s connected to the 1s, but it's not wrong to do that. Like, you would still get full credit if you did that. Especially if you're drawing this set right here, it would make more sense to connect it then, because this set is only possible if we mix our 2s and our 1s, or our 3s and our 1s. Like, I couldn't get this overall MO if I didn't mix them. So whatever the principal quantum number is, that one's most likely going to interact with the 1s of our hydrogen if it's within the energy bounds. Here, try to clearly illustrate, we have another orbital down here. This one won't interact with it. But I do have the energies if you wanted to know somewhere. I have them on a piece of paper in my hand somewhere in this notebook. Yes.
So SP mixing is sigma pi mixing,
Yes.
not like s orbital.
So that's actually what it means, but it means like the sigma of our 2p orbital, right?
Okay.
Yeah, so
I was just getting
sigma and
confused because
pi of our
I thought you
2p.
meant, like, the 2s would interact with the 2p.
No, so I actually have an image of it because I have a feeling that this was going to be illustrate what I meant by the SP mixing.
And also, is there like a rule for when the sigma 2p would be below the pi 2p? Like,
Oh yeah, so it's going to be in cases of O2, F2. You said sigma 2p,
yes,
right?
okay,
Yeah,
I see
those
that.
ones.
Yes.
So
Okay,
I
thank
think I am connected now.
Isn't it just after nitrogen?
Yeah. So here's the actual reasoning why, like, if you wanted to see it illustrated out, here it is. So what we see is this is our sigma 2p right here. It goes down in energy as we get further, and then it flips at our N2. So this is just the exact same trend, and when we're talking about heteronuclear, typically has the case of this type of high mixing. Alrighty, any other questions on number 9? Cool, we're almost there, one more. Alright, so they gave us a reaction. They want to know whether this favors products or reactants, if it's at equilibrium. What do we think? Well, let's start off. What is palladium? If I asked you to classify palladium 2+, what would you classify it as? Yeah, it's a soft acid. What about NH3? What would you classify that as? Hard or moderate? I would take either one. So this is a moderate base. What about Cn-? Hard, soft, moderate. Soft base. So chemists are easy. We like to use easy rules. Likes like to interact with likes. So soft likes to interact with soft. So here we have a soft-soft connection. Here we have a soft moderate connection. Which one do you think is a stronger, more stable species? PDCN or PDNH3? Yeah, because we have a soft-soft interaction. So this means that we're going to favor our reactants because PD2+ is a soft acid. So it prefers to bind with soft bases.
Is that another thing that we're just gonna do? Kind of just gonna have to know, okay, this is what's soft, this is liquid. Nobody knows something.
Typically, I like to think of soft things as large and polarizable. If we look at our periodic table, there's also kind of a trend, not really, but kind of a trend. This is not a hard rule, so please don't take this as a hard rule.
I thought it was like on one side of
Yeah.
the iron and the other side.
So yeah, things typically in like this region, like this region right here are softer. Not always, but are typically softer. Things in this region are typically harder, and we can also reason this out because they have higher oxidation states in our earlier transition metals and less oxidation states in these transition metals, right? Like zinc really only has zinc 2+ that it really likes to be in. Same thing with cadmium, mercury. Like we could have mercury plus, but it prefers a 2+ oxidation state. So things with lower oxidation states are typically softer. Things with higher oxidation states are typically harder. So that's why Fe3+ is a hard acid, but Fe2+ is a moderate acid.
For the elements you look here, like the boron, copper, so would those, for the most part, be considered to be soft?
So that trend only is true for the transition metals. Once we get over here, oxygen, nitrogen, fluorine are all harder bases, and then sulfur, iodine, and bromine are a bit softer. So it changes up a little bit in that area. Alrighty. So yeah, it prefers to bind with soft bases, such as CN-. And then, short rule of thumb, soft acids / bases are large and polarizable. So that's not really part of the answer. That's more just like, this is how we know these things are soft. We don't just need to memorize things. We can just look at it and be like, well, this is a pretty large atom. It's polarizable. Gotta be soft. So I think I answered this one earlier, actually, but let's talk about it. What type of ligand is NH3? How can it interact with a metal center? What was that? Oh, that's okay. Well, I'll give you a hint. It is this type of question. There's only one right answer here. Everything is a sigma donor. So if it was a pi acceptor, it's also a sigma donor. If it's a pi donor, it's also a sigma donor. Everything is like all our ligands are sigma donors. Like they have to interact with our metal center somehow. So they're all sigma donors. But what plays a role in our spectrochemical series, things to the left, well, I think of it to the left. That doesn't help because it's not really left and right on your sheet. But things up here, so iodine, bromine, sulfur, thiocyanate, these are primarily pi donors. Things down here, cyanide, carbon monoxide, are pi acceptors. And then things in the middle are sigma donors. So here, NH3 is just a sigma donor. It doesn't do pi acceptance or pi donation. If I asked about cyanide, you'd have to circle two options because technically there are, it is a pi acceptor, but it's not wrong to say it's also a sigma donor because it is. And then the last one is, why is cyanide a strong field ligand?
So if I just wrote pi back bonding,
I'm looking for three things here. So pi back bonding is one. What type of donation does it do?
pi acceptor.
It is a pi acceptor. What about sigma? Sigma donor. So to really strengthen your answer, if you wanted to, you could draw the interaction between the two. So like if I had my d orbital for my metal, this is typically like dxy that it is, and then my cyanide ligand, what I would see is donation from my filled dxy orbital. It's not always dxy, but most oftentimes it is our dxy orbital into our empty pi star orbital. So this would be like a metal dxy or one of those like flower-looking orbitals from our metal. And then this would be into our pi star orbital of our ligand. And that's what that pi back bonding is. Well, sigma donation is the other way where it's going this way into our metal. So they're two different things. They don't go in the same diagram. If they go in the same diagram, this would be a different type. This is like our phosphorine or triphenylphosphenes, how they interact. That is not pi back bonding. This is pi back bonding. Yes, this. I have a better image of it, but not here.
Explain what pi back bonding is, because I know that CN and CO have pi back bonding, but I wouldn't know how to say what pi back bonding is.
Pi back bonding is when we take a metal d orbital, primarily the dxy, dyz, or dxc, and it donates, so it's a filled d orbital of our metal, it's donating electrons into the empty pi star orbital of our ligand.
the HCl one and figure out why like the other practice exam had the 2p connecting to 4 different things?
Yeah, let me pull up. I'm gonna stop this recording.